Chapter 7, Section 5 is about using the proportional relationships that we've dealt with for the past couple sections. By the end of this lesson, you should be able to use ratios to make indirect measurements and use scale drawings to solve problems. So indirect measurement is any method that uses formulas, similar figures, or proportions to measure an object rather than actually breaking out like a tape measure and measuring something. A scale drawing represents an object as smaller or larger than its actual size, and the scale is the ratio of any length in the drawing to the corresponding actual length. And this is something you see all the time on a map. So on a map, it's obviously not real life size. It might say something like an inch represents 1,000 miles if you were looking at a big map. So if we talk about some indirect measurements, Tyler wants to find the height of a telephone pole. So he measures the pole's shadow and then his own shadow and made a diagram. And the reason why he did this is because he can figure out his height easily, and then because these are similar figures, we can use proportions to figure out how tall the flagpole is. Now, one thing we need to be careful when we solve a problem like this is that these heights are in feet and inches. And the English system kind of sucks here because we can't just write 5.9 because it's 9 inches. So what we're going to do is just change everything to inches. So remember 5 feet is really 60 inches. So he is 69 inches tall, and 7 feet is really 84 inches plus the 8. So his shadow is really 92 inches long. We'll find the height in inches of this flagpole, and the shadow for the flagpole is 38 feet, which is 456 inches plus 4 for a total of 460 inches. So now that everything is in appropriate units, we can set up proportions. So there's tons of different ways to do this. I'm going to use the height of Tyler divided by his shadow and set that equal to the height of the flagpole, which we don't know, divided by its shadow. We don't really need the units here because when we cross multiply or find the cross products, we're just going to multiply the numbers together. So we get 92h equals 460 times 69, which is 31,740. And then if we divide both sides by 92, we end up with 345. And remember, these are inches. Now to double check that our answer makes sense, I'm going to change that into feet. So 345 divided by 12 gives me 28.75. So 28.75 feet means that I have 28 feet and then 0.75 of a foot, which is really 9 inches. And then double check that your answer makes sense. This guy's shadow was longer than he is tall, so it would make sense that the flagpole shadow is longer than it is tall as well. So let's do one with a map. On a Wisconsin road map, Kristen measured a distance of 11 1/8 inch from Madison to Wanusu. The scale of this map is that 1 inch is 13 miles. What is the actual distance between Madison and Wanusu to the nearest mile? So we can set up our proportion. She measured a distance of 11 1/8. And instead of writing that fraction 1/8, I'm going to write it as a decimal, which is 11.125. And I don't know the actual distance, so let's make it x. But I know that the map tells us that 1 inch is the same thing as 13 miles. So once we set up our proportion, we can find our cross products, and this is a pretty easy one. We get that x is 13 times 11 1/8. So we get 144.625. But they tell us to round it to the nearest mile, so this is about 145 miles. Let's try something else. Lady Liberty holds a tablet in her left hand. The tablet is 7.19 meters long and 4.14 meters wide. If you made a scale drawing and the scale was 1 centimeter equals 0.75 meters, what would the dimensions be to the nearest tenth? So we're going to have to do length and width. So if we talk about length, we know in real life it is 7.19 meters long. We don't know how long it's going to be on our scale drawing, but we know that 0.75 meters is the same thing as 1 centimeter in our scale. And if you notice, they gave it to us kind of backwards, but we're lining up real life and our model. So then we find our cross products. So we get 0.75x equals 7.19. So x has to be about 9.6 centimeters. So remember, that's just the length. And then we got to figure out the width, since this had 2 dimensions. So our proportion is going to look almost exactly the same, except the 4.14 meters. But then our scale is going to be exactly the same. And if we find our cross products for this one, our equation almost looks the same, except for the 4.14. But we'll solve the exact same way. And we end up with the width having to be 5.5 centimeters. So with this model that we're going to make, we want the tablet to be 9.6 by 5.5 centimeters. Alright, so in similar triangles, there's a relationship between the similarity ratio, the perimeter ratio, and the area ratio. So if I gave you these 2 triangles, ABC and DEF, and I told you they were similar to each other, we should be able to make a similarity ratio. That's old news. But the perimeter ratio is always the same as the similarity ratio, because remember, that just compares the sides. So if you happen to add up all the sides, you're going to simplify down to the same fraction. The area ratio is related to that because it is whatever the perimeter ratio is squared. And in this case, we did areas 1/2 base times height, and we figured out what the area for both of them were. And in this case, we got 1/4, which is 1/2 squared. So, of course, we have a theorem. If the similarity ratio of 2 similar figures is A over B, then the ratio of their perimeters is A over B, and the ratio of their areas is A squared over B squared. And then, if you remember back to Algebra 1 when we talked about exponent rules, those 2 things mean exactly the same thing. You can square the numbers on top and bottom, or you could put parentheses around them and square them. So for this one, it tells us that these 2 triangles are similar. So we can find their similarity ratios with the 2 pieces of information that were given, just a side length, because this theorem back here tells us that your similarity ratio is exactly the same as your perimeter ratio. So we're going to use that. So the similarity ratio, let's do 13 over 9.1. And since we can't simplify that, let's just leave it. We know that the perimeter ratio has to be exactly the same. Has to be 13 over 9.1. So that means that our perimeters have to match up. So since we use the 13 from this, we'll use the perimeter for that one on top, divided by the 9.1, which is the perimeter of whatever this guy is, which we don't know. And then we solve it just like all of our other proportions. Find your cross products. So 13x and 36 times 9.1 gives you 327.6. And if you get x by itself, you end up with 25.2. So that's the perimeter of this triangle here. Now, the area ratio is a little different because area ratio is the square of the similarity ratio and the perimeter ratio. So it is these two multiplied together, or both top and bottom squared. So instead of 13 over 9.1, it's 13 squared over 9.1 squared. So I'm just going to simplify that. 13 squared is 169, and 9.1 squared is 82.81. Now this is what the area has to be proportional to. So again, just like all the other ones, we can set up a nice little proportion. So since 169 is the length of this squared, we got to put the area of that one on top, divided by the area that we don't know here. Do some cross products. So I'll do 60 times the 82.81. 4,968.6. And if we divide by 169, we get that the area is 29.4. Should be centimeters squared. So using this theorem here, we can figure out the perimeter of a triangle and the area of a triangle. So here's another one. ABC and DEF are similar, and then they tell us all these measurements. I'm going to draw myself a picture. So ABC is similar to DEF. We'll draw them in the same order. From B to C, they tell us is 4. From E to F, they tell us is 12. And then they tell us the perimeter for this one is 42, and the area is 96. We have to find the perimeter and area for ABC. So in order to do that, just like before, we need to set up a similarity ratio. And I'm going to set it up backwards. So DEF over ABC will be 12 over 4, which is 3. So in order to figure out perimeter, remember the perimeter ratio has to be the same. So we could write 3 over 1. Since the 3, we started with this triangle and then went to that one, we got to do the same thing with the perimeter over the x that we don't know. And then this problem's a little easier to solve. 3 goes into 4 once with 1 left over, and 3 goes into 12 4 times. So the perimeter of ABC has to be 14 millimeters. And then remember, area has to be squared. So instead of 3, it has to be 3 squared, which is 9. So for the area, we want 9 over 1 to equal this area, which is 96, over what we don't know. So 9x equals 96. 9 goes into 9 once, and it goes into 6 no times, but then there is some leftovers. So we end up with the area being 10.67 millimeters squared. So when you get a problem like this, make sure you draw yourself a picture. It'll make your life a lot easier. So you should be able to use ratios to make indirect measurements. This was the first part. That was a lot easier. And then use scale drawings to solve problems like we just did with those two theorems. Make sure you write down any questions you have, and we can go over them in class tomorrow. Have a good night.